what I should remind people what Moore's law is about, it is not about number of transistors doubling every year or 2 years. It's about the density at which you get the best cost per transistor doubling every 2 years. Companies are not building denser and denser circuits because they want, to amaze us, but because that's a way of reducing the cost per function. And for many years, indeed, the cost per function would go down, would favor denser and denser switches, denser and denser, chips, and roughly every 2 years, whatever. And that can stop for technology reasons, which you keep hearing. We don't know how to build smaller transistors. And it can stop for economic reasons, that further reducing the size of transistors doesn't reduce the cost per transistor. And it's probably the first one, both are relevant. It's generally agreed that we won't go beyond 7 nanometer with the current technology, and that's about 2024 by current predictions. But the other one also is happening, has happened. It seems that we're not gaining additional reduction in cost by going to denser circuitry. And in that sense, the economic end of Moore's law is already happening. Very briefly, you probably have heard that many times. There was, at a time when I was a student and learned about VLSI, there was this nice rules that you decrease the feature size, the size of your transistors. If the feature decreased by a factor of 2, then you could put 4 times as many transistors on a chip, and you could decrease the clocks, or you could increase the clock speed by a factor of 2, and everything went fine, and the power consumption would not change. So that's the golden era of Dennard scaling. And the other point is that, and that's still true today, the other point is that the main cost in chips is not the variable cost of manufacturing individual chips, but is the fixed cost of building the factories and designing the chips and testing them. So even so, cost of manufacturing chips and cost certainly of building factories has increased a lot. Vendors could compensate by having higher and higher volumes so that they could keep roughly the price per chip constant just by increasing volume. And that has not happened now for a dozen years, basically because of leakage current. So we cannot continue to reduce voltage as fast as we did it. We needed a lot of new technologies, new materials, new device geometry. Transistors are not anymore flat, they are standing up. We are using new materials, strained silicon, high-K metal gates, and so on. And manufacturing costs have increased quite rapidly. Also, industry had wanted to move from the current lithography technologies that uses I think it's about 200 nanometer wavelengths, has wanted to move to ultraviolet, but it's not happening, or it's not happening fast enough. So the slope has decreased. For a while, we are not moving at the slope that was decreed by Moore. It has decreased, and it has decreased, and it has come at the expense of a lot of new technologies. It has not been just if we know how to do lithography as a finer scale, everything works perfect. We have needed a lot of new inventions. And, more layers, more complex geometries, more materials, new types of materials, feature size smaller, and there is more variance in the manufacturing, in the materials. So you need to accommodate higher manufacturing variance. I don't know if you are aware, but on a modern chip today, you accommodate, you provide different voltage for different areas of the chip according to accommodate manufacturing variance. Packages are more expensive. Number of transistors does not increase proportional to the square of the feature size. For one thing, because you still need wide wires to feed everything. For another reason, because when you go to lower voltage, lower charges, you need to increase the distance between your gates to avoid interferences. As I said, EUV lithography is not yet in wide use. And the other point which is very important, the ability to producing larger volumes of same unit are disappearing. A lot of the volume manufacturing today is cell phone, and cell phone vendors want more specialization. So it's not anymore, I build the next 86 and I can sell billions of it. The ability of going to larger volumes is limited by the desire of industry to having more specialization in the devices that they are buying. That's one interpretation of the market, comes from, I don't remember the company, that is on business strategy, international business strategies, which essentially is plotting the cost per function. I don't know exactly how function is defined here at different feature sizes, going from 90 nanometer to today we are at 16, 14 nanometer, and the next technology will be 10 nanometers. And the point is that as they believe that the cost per function is not decreasing anymore, and that's a reason some vendors have decided to stay at, at 28 nanometer, because further decreasing feature size doesn't improve the cost performance of the devices. So you may want to do it just to have, faster chip or more cores than your competitor, but as a general way of getting better cost performance, it seems to have run out of steam. Intel believes otherwise, but Intel is not publishing its numbers, and Intel certainly is trying to push the advantage of having more advanced technology as compared to other vendors that are using foundries. But there are other symptoms that we're getting to the end of the road. Here I plotted the number of companies that are doing the most advanced technology. And if I go ahead one more, there will be only 4 left because STM has gone out of the race. So the number of companies that can build the most advanced devices is decreasing. Same thing, I won't spend time on that, for DRAM manufacturers. We're left basically with 3 companies that are building the most advanced memory devices. So CMOS is slowing down, but the other thing to remember is that CMOS, there is no replacement in place now for CMOS. When I'm old enough to remember the shift from gray machines that were using ECL technology to clusters built out of MOS microprocessor. And Cray and ECL technology was getting to the end of its life, and they were looking at gallium arsenide and so on. But there was a replacement in place because MOS was already used, Intel was already in existence. And there were devices, and there was an expectation of continued growth of the, in the density of CMOS, or MOS at the time, and MOS. But today there is no technology which is ready for use, that has gone out of the lab and is moving into production. It typically takes 10 years to move from lab to production. So I can predict fairly safely that general purpose computers will continue to use CMOS in the next decade. And even worse, there is no technology that promises to be better. That's from a paper by Nikonov and Yang. They look at the energy delay product, which is a measure of the quality of technology. And that's for a 32-bit adder, what you're seeing here. And what various technologies are giving or promising to give. And they are at different places in the spectrum of energy. Some are slow but use less energy, some are. But the point is that the energy delay product is not improved over CMOS, over what CMOS is or can be soon. Basically, well, essentially, we have no technology that promises to be better. With one possible exception, which is tunneling, Josephson junction, or whatever it's now called, but quantum tunneling devices might produce better, run much faster at lower energy. So it is entirely possible that no general purpose technology will replace CMOS. Yes, you will have neuromorphic computing, you will have quantum computing, you will have a variety of general technologies, but it's entirely possible, that we shall stay at wherever we are in 10 years from now in terms of silicon technology. Now, predicting more than 10 years ahead what technology will do is always dangerous, but predicting that it will do miracles is as dangerous as predicting that it will stay in place. Okay, so what does it mean, and what does it mean in terms that interest you? Energy. So the point that I want to make is that it's entirely possible. First, we can go on, we can continue to improve for a while the power of our supercomputers and the compute power per energy ratio of supercomputers. But what it probably means that we have to go to more and more specialization in the architectures of supercomputers. When we moved away from Cray vector, we moved into cluster of workstations. And the reason we did that is because the workstation technology was evolving very rapidly according to Moore's law. If Moore's law is not promising anymore this rapid evolution, the reasons to build supercomputers out of commodity components weaken, and the justification is disappearing, at least when it comes to what's the best way of getting some level of performance. Before, our game was just to keep up with the latest Intel or IBM or whatever chip. Now, these chips are not moving fast in performance. We can start thinking what we really need in order to build performing supercomputers. And in fact, we have already more and more specialization in supercomputers. Xeon Phi or high-end GPUs are used in more than supercomputers, but they are not general-purpose engines. They are used for high scientific computing, high-performance scientific computing or high-performance signal processing. There are markets, the markets that are driving Xeon Phi or high-end GPU are smaller than the markets that were driving general-purpose microprocessors. And there are other things. As you probably know, NVIDIA has fought for many years the HPC requirement of putting ECC in their memory. That's an example that, even it took, I don't remember, but 3 or 5 years for them to eventually put ECC. So the integrated adapters, we do more and more, we already do more and more specialization in our HPC platforms, at least on the hardware. And it's fair to ask how far it will go. And here is, proof by top 500, the usual way of proving statements on HPC. I put the top 5 machines from the November top 500. And as you know well, the top player is China with Sunway, which uses a special purpose CPU that they designed specially for this machine. And it's also interesting that the fourth one on the list, the BGQ, is bare comparison. What I plotted here, by the way, is petaflop by megawatt. And that's a figure of measures that I use here. So Sunway is clearly way ahead of competition in terms of petaflop per megawatt. And clearly, using a special purpose microprocessor is a large part of that, especially since they don't have access to the latest and greatest design technology. Apparently, they're using 28 nanometer technology for their engine, whereas our current, the fastest US machine, or one of the fastest US machines on this list, Corey, is already using 40 nanometer. So it's impressive that they can get twice as much petaflop per megawatt using a technology, which is 2 generations back. And you see the same thing with the BGQ. The BGQ compares in the ratio of flops to watts. It's comparable to the Titan or TNA2, but it uses a technology which is, again, 2 generations back. 45 nanometer is a technology of BGQ, which is 2 generations back. So picking that as an example, roughly using a specialized core gives you the same advantage as 2 generations of device technology. And if device technology is not making progress, then again, people will use more and more specialized cores to get the same performance. So I believe that specialized nodes are going to become more and more the norm. In fact, I am afraid the first machine to reach Exascale will be a Chinese machine using a specialized node. And one of the reasons neither US nor Europe are moving aggressively in this way, I think, is more political than technological. The IBM, Intels, or Bulls of the world don't want necessarily to get money to work on specialized cores. They prefer to get money to work on their conventional designs. And they don't want to manufacture specialized machines. They want to manufacture general purpose machines that have a broader market. I understand them. And politically, it's better in the US for the people that push for HPC to claim that they help the industry at large, rather than claiming, we are going to build unique devices that are going to run faster. But at some point, the HPC community will have to, decide, whether it is in the business of helping the general IT industry building newer chips or is in the business of building the fastest possible machine. Okay, energy. Energy, what specialization gives you is, as you know, and I don't need to repeat it, the main impediment to performance of supercomputers today is their energy consumption. Energy consumption comes mostly from moving data around over long wires. So what can you do with specialized devices? First, you can get much denser packaging. You can, and that reduces the energy consumption. You can compute closer to memories. That has been supposedly one of the big advantages of the memory cube technology of Micron. You can replace caches with scratch pads. Specialized compute devices typically will not have caches with each of the cores, but they may have a cache for the main compute engines that can be a regular ARM or a regular x86, but most of the compute devices will not have caches. If you think of a GPU, you learn it has a cache, but it's far from being a cache in the way you expect a cache on a regular CPU. It's more really a buffer in between the memory and the compute engine. There was a project at Intel to build a machine without caches. Their estimate was that they gain a factor of 2 in energy consumption by replacing caches with scratch pads. And of course, you can have specialized compute engine if you have a proof that an FPGA can compute something faster or a specialized device of one kind or another. You hear about companies building specialized machine learning devices. We had in the past experience of building specialized devices for scientific computing, in particular for molecular dynamics. We know we can do computations with much less energy once we specialize the devices. By the way, I didn't discuss this diagram. It's a diagram from a talk of Bill Daly several years ago, basically showing how much energy you spend moving data across a chip. So working on doing double precision, and that's 2 or 3 years old by now. Doing a double precision floating point 60-bit is 20 picojoules. Moving data across the chip, going to SRAM is 50 picojoule. Going to DRAM is 60 nanojoule. So you have basically 3 orders of magnitude difference between what it takes to do computation and what it takes to go in memory in terms of energy. And that's what is driving, I suppose, much of your thinking here. So here are some examples of specialization technologies. Again, I assume you are familiar with most of that. That's high bandwidth memory. High bandwidth memory uses 3D packages where you put multiple memory chips one on top of another. It consumes 1/3 of the energy of DRAM, so very big gain in terms of energy, but it's restricted now to 8 gigabyte, maybe tomorrow to 16 gigabyte. So you give up volume of memory against energy. Of course, the other big advantage of high bandwidth memory is that its bandwidth is much higher. That's the name, after all. I don't remember the exact ratio, but it's certainly 4 or 5 times faster than DRAM or higher bandwidth. Yeah, the total, if you put multiple, you can put 8 gigabyte on a package today, on whatever you call it. Thank you. You put 4 around, you processor. Each one has 2 gigabytes, so all in all you can have 8 gigabytes, and presumably it will shift. The next standard speaks of 16 gigabytes. Another example, when we say that we cannot increase that far chip density, there are contrarians that say it's not a problem to increase chip density because you can build more and more layers on your chip rather than having 8 or 32. Maybe you have 100 or so layers on the chip, so you can have many more devices on a chip. Of course, the downside is that you cannot use all of them at the same time because you cannot power or you cannot cool such a device. Clearly the notion of multi-layer silicon implies a notion of dark silicon, that you can have many different engines on one chip, but at any point in time you are using only some of them. And that may be a direction that industry will move to. Certainly technology that is being developed, I think, by a project paid by European Union and by a project in US, or at least one project in US, is a notion of being able to put on an interposer many small chips. Disadvantage is that you go out of the chips. Advantage is that it costs still less than going to the package. And the interposer can also be dynamic, doesn't have to be static. So you can deal with, you don't need as much power at your interface. And of course, when price will allow it, it could be an optical interposer rather than metal. And the idea is that with this technology, you could build a system that integrates many different specialized engines in one package, one tightly coupled package. And this is technologies, as I said, that I know is being explored in several countries. Another idea that may come back is cryogenics. You can run, I keep saying that the problem is less power, more cooling. You cannot bring the power out of a chip. Well, once upon a time, we had machines that were cooled by fluorine art or liquid nitrogen or what have you. That may come back. Interestingly, CMOS can be much more power efficiently if it works at a very low temperature. If I understand from my friends, the main problem is that you may need different design rules to design CMOS circuitries that runs at cryogenic temperatures. But that's a way in which you could get much better performance out of CMOS devices. But let's take this question, let's look at this device, or this kind of device, and let's ask a question. Suppose that you need to have an alphabet of 20 or 10 or 12 building blocks, and you will be able to assemble your supercomputing nodes, by combining in whichever way you want, in whatever quantity you want, these dozen of building blocks. What will be the building blocks? What are the main operations we would like to customize in a supercomputer node? And it's an open question. I don't know the answer, and I think it should be an interesting research question. We know vector is a good thing. We're using it. SIMT is perhaps a little better than vector. If you think of a GPU, essentially it has a macro data flow engine that schedule macro tasks onto the compute nodes. There are discussions on macro data flow architectures of one kind or another. That may be another direction. Sure, we want scatter-gather near the memory because our codes are increasingly irregular. What else? Do you want an FFT engine? Do you want a molecular dynamic engine? I think, starting to think in these terms is important for research on future energy-efficient supercomputers. Software implications. Software implications, power is a bottleneck, you know that. First implication is be ready to use hundreds of millions of threads. No, we don't have a way of avoiding it. We are already in the millions of threads. We shall be in a year or two in the 10 millions, and we shall have to be at hundreds of millions at exascale because threads are not running any faster. In fact, they tend to run slower these days. The other point is that not everything will run at the same speed. You already have turbo power on Intel chips, and it's becoming even more marked in the future. And you cannot run all the processor at full speed on a future machine. So some will run faster, some will run slower. And the unfortunate thing is that you don't always know which run faster, which run slower. And you will have to manage that equal work doesn't mean equal compute time on future cores. And I think I have, and of course, communication is where you consume energy, as I already said. So communication efficient algorithm is what algorithm designers are going to work for the next years. But let me give you some concrete examples, and that's on experiment. I don't remember on an Intel machine, but I don't remember which one. And the point is, if we run on each core DGEM, we get 285 gigaflop on this machine. If we run only one core, and only that core is running, and this core is doing DGEM, we get 23.7 gigaflop. If you multiply 23.7 by 32, it's much more than 285. So 32 cores don't run 32 times faster than one core. Keep that in mind when you design your algorithm. That number 13.7 is when only one core ran DGEM, but the other cores were still active. So, when you speak of future machines, you have to be careful about how much performance you expect by having more cores. Your limit is not the number of cores, your limit is your budget, your energy budget, and how many operations you can do. The other thing to keep in mind, identical CPUs are not identical. That's an experiment, again, with the same type of machine, which unfortunately I don't remember, running the same stress test on two nodes, which have the same specification, same model number, what have you, but they behave totally different. One is a blue and one is a green. So you see that you can have, what is plotted is a temperature per core, 16 cores here. And you see that for one stress package, green gets to a higher temperature. Here you get another behavior. So, things are somewhat stochastic. You don't control fully the power management and the temperature of your chips. So yes, you will need less synchronization. Yes, you need to keep in mind that computation time now become stochastic. It's not deterministic anymore. And keep in mind that on future machine, you may be able, now when you think of load balancing, you think of moving computation from one core to another. In a future machine, rather than moving computation from one core to another, you may be able to move power from one core to another. It's almost possible on the latest Intel machines if you get access to the right hooks. And moving power from one core to another is cheaper than moving applications because you don't have the problem of moving data from one cache to another. So think that you have now two knobs for load balancing, moving computation and moving power, or reallocating power. Again, a message that you probably heard many times: vector better than scalar, single precision better than double precision, half precision better than single precision in terms of power, because you get more flops, because you use less memory, because you are moving less data from the memory to the CPU, because you take less space in your cache, so you have better cache heat ratio. And experience bears that. That's some research I was involved with. What you have here is two examples of using an inexact Newton method. Let's see, blue is double precision scalar, green is single precision scalar, yellow is double precision vector, and orange is single precision vector, and you have the energy consumed. So you see, going from double precision scalar to single precision vector, you're getting a factor of 8, I think, or 6 or 8, whatever is the ratio between those. Of course, it's application dependent. Here is an application that is doing slightly less well, or it's the same application with a different input. Here, but still there is a factor of 3 or 3 point something. So using single precision where you can, and using, of course, vector when you can, is a huge advantage. Another way of thinking, by the way, of single precision versus double precision is a reverse formulation. If you have a fixed power budget, what's the best way to get, or what's the best result you can get? That's, in this example, is again iterative or inexact Newton, an iterative solution. And the question is, for a given power budget, what's the best accuracy you can get? And that's an interesting question, and we have one paper on that, but far from having solved the problem, it's still fairly open. But it shows that we started here with a double precision solution. We could get, within some power budget, energy budget, we could get an answer which is accurate to 10 minus 6. By doing more iteration in single precision and then moving to double precision, reusing, if you wish, the saved power budget, we could get within the sum power budget to 10 to minus 10 accuracy in the answer. So that's another way of thinking of how you use. So in other words, rather than as today thinking how much I can compute within a given time, increasingly the question you should ask is how much I can compute within a given power budget. And for iterative solutions, there are many ways, there are many ways of making this trade-off, and they're different than just reducing compute time. Anyhow, that's a story. I said that Beyond-CMOS may not happen for a while. If it happens, I picked that from one of the latest one of the last ITRS reports. It's a huge word there. What could happen, how you represent a state, is it an electrical charge, is it a state of a molecule, whatever, what materials you are using, how you build devices out of it, how you represent data. Yes, innovation can happen beyond CMOS. That's not my point. My point is that I shall be retired long before innovation that goes beyond CMOS will impact high-performance computing. And I'm afraid that may be true of even people that are younger than I. So to summarize, we are still far from the absolute limits of computing. Well, probably 5 orders of magnitudes off from the theoretical limits of computing, and there are many interesting ideas on how we could compute with less energy. The bottleneck is not the laws of physics. The bottleneck is what's feasible from a technology viewpoint, what's feasible from a manufacturing viewpoint. You know, can we manufacture devices that are much faster than current transistors at the same cost or lower cost that we manufacture transistors today? So I think we're close towards practical limit of mass-produced cheap computing devices. And we may probably swing one more decade with more specialized architecture and devices. I'm not sure if there is a path away, maybe, maybe molecular computing, maybe there are different ideas that are interesting. There is a non-general purpose like quantum, or they are not, they are not yet even at the lab stage, like molecular computing. But there is another way of getting supercomputers: spend more money. And the French here should be familiar with one facility that is costing $20 billion and consume 110 megawatts. So my question is, when there will be, is there somebody that is willing to make the case for a 20 billion, 110 megawatt supercomputer? Give me more money, I shall build you a larger machine. And the point that I want to emphasize here, because supercomputers have become cluster of commodity devices, we have stopped thinking of supercomputers as unique scientific devices. Now, we think of them as bigger clusters, but not as unique scientific devices. When supercomputing started, physicists like Wilson or other people like that went and say, we need supercomputers to advance science. And I don't think that today Nobel Prize physicists or chemists are going and are saying, we need to spend a few billions to build a faster supercomputer to advance science. And part of what is needed to continue with supercomputing is to make the case that we care about performance. It's not only a top 500 or a game, or will be first to Exascale, but it is a game of advancing science that needs more powerful scientific engines. Thank you.